Hi, I'm Yvonne. I'm a PhD candidate at the Karlsruhe Institute of Technology. This is a pre-recorded presentation for the 2021 meeting of the Society for Mathematical Psychology. I will talk about the influence of the place value system on symbolic number perception in a ruler task. I will start with explaining some background on number perception, then go over to identify the problem of non-correspondence between symbolic and non-symbolic numbers, and then discuss a modeling approach that provides a solution to the identified problem. So we were interested in how people perceive numbers, and there are different ways in which numbers can be noted. The most basic type are non-symbolic numbers, noted on the left here. In studies of non-symbolic number perception, they are usually noted in these dot clouds. The magnitude in these clouds can already be distinguished by children and animals. So they can, for example, distinguish which dot cloud contains more dots. Then there are symbolic numbers, the ones we learn in school based on Arabic numerals. If people estimate how many dots are on the left side without counting, most people estimate something around 13. Estimating 12 is also likely, because it is an established finding that people underestimate the number in non-symbolic stimuli. Interestingly, children also underestimate the magnitude of symbolic stimuli. For example, if you give them a ruler with 0 on the left side and 100 on the right side, they will not put 50 in the middle. Instead, they will put it on the far right side of the ruler, ultimately giving more space to smaller numbers. Children do this until around 3rd or 4th grade, until they start to make linear estimates. This has been called a developmental shift. It is assumed that non-symbolic and symbolic numbers are mapped to the same mental analog representation. This is how number perception works according to Duhan. Magnitude estimation is supposed to happen on this mental analog representation. And the compression, which leads to underestimation, is also supposed to happen on the level of the mental analog representation. This can explain why there is compression in both non-symbolic and symbolic magnitude estimation. However, there are two problems with this. First, the compression of non-symbolic numbers in adults looks like this, according to Inno and Ida. It is a power function with the exponent 0.87. The y equals x line indicates linear mapping, meaning no compression. In contrast, the compression of symbolic numbers is usually only substantial in children below the grades 3 and 4, so this is ages 8 to 10, according to Ziegler and Opfer, and it looks strikingly different from the compression of non-symbolic numbers. It is a logarithmic function with the scaling factor 99.8. As already mentioned before, children overestimate the magnitude of small numbers and underestimate the magnitude of large numbers. As can be seen on the plot, the lines of the best-fitting functions are far apart and of different shape, something that one would not expect if the compression stems from the same source. Second, while children's estimate of symbolic numbers become more linear with age, non-symbolic estimates do not become less biased in adults. Adults do get better in making non-symbolic estimates, of course, but the only thing that decreases is the noise, not the bias. If the two number formats share the same compressed internal representation, it is unclear why there would be a developmental change in one of the formats but not the other. Now the question is, why are they looking different even though they are meant to be the same? We hypothesized that something else is contributing to the compression in symbolic numbers, which is not the shared mental analog representation. We think it is likely that the estimates of symbolic numbers of children are distorted because symbolic numbers are noted in the place value system. Numbers in the decimal system have three key properties, one of which is place value. The first are the number of elements or figures, so the number 13 has 2 figures. The second are the type of elements or the numerals. 13 has a 1 and a 3. Finally, the position in which the elements are placed matter. The 1 in front indicates 1 times a 10 and the 3 on the right indicates 3 times a 1. The first two properties are easy to master, but the third is more challenging. To understand it, one has to know that the position of an element matters and that the number space increases exponentially with each additional numeral. This is a graph that illustrates this. With one-figure numbers, you can represent the numbers from 0 to 9. With two-figure numbers, you can represent the numbers 10 to 99, and so on. The number of numbers you can represent increases exponentially with each numeral added on the left. Using 5 figures, you can represent 90,000 numbers. This notation has been useful because it allows for the notation of large quantities on little space. So, for example, I can write the number 1000 with 4 symbols, but I'm not sure I could fit 1000 dots on this slide here. The point is that the decimal system, or really any number system that uses place value, is a compressed system. And we think that the logarithmic-looking compression for symbolic numbers observed in children actually comes from that. So, how does the place value system shape the estimates of children? As I already said, the first two key properties of numbers are easy to master for children. They just need to learn to count and distinguish between 10 symbols. What is actually hard is to understand place value. Even for adults, it is difficult to understand how exponential growth works, and it is often underestimated. So if we assume that children in second grade only understand the first two properties, we can make predictions how their estimates will look like. If children can understand the first two key properties of number, but do not yet understand place value and assume linear growth of number space instead of exponential growth, they will assume that there are equally as many numbers between 0 and 10 as there are between 10 and 100. This means that they would place the number 10 on this ruler somewhere in the middle. Extending this idea to a scale from 0 to 1000 makes the distribution of estimates look logarithmic in shape. Based on this, we hypothesized that misunderstanding of place value can lead to logarithmically compressed estimates, just as observed. To test this, we conducted an experiment with adult participants in which they had to make estimates on an unfamiliar place value system. Here is what we would expect, according to the theoretical approaches mentioned before. A. If non-symbolic and symbolic numbers are mapped to the same mental analog representation and compression happens on that level, we would expect estimates of symbolic numbers to be compressed like a power function. B. If there is a developmental shift and adults become more linear with age, independent of the underlying place value system, we expect the estimates to be linear. C. If what we think is correct and the place value system systematically shapes magnitude estimates, adults will show logarithmically compressed estimates. And finally D, we also think that we can create a model that assumes linear growth for each additional figure, which will make good predictions. So how does a task with an unfamiliar place value system look like? These are the instructions from our experiment. We use two different scales, one base 26 and one base 5. Instead of using numerals like in a decimal system, we use the letters from the alphabet, because the order of them is familiar to everyone, but people are not used to calculating with them. In this way, the task is similar to the challenge that children face. The adults can distinguish between one-letter indices and two-letter indices, and they know that B comes after A, but they are not familiar with the underlying place value system. As indicated in the instructions, participants had to place different indices on the slider. These instructions are taken from the base 26 task, in which the scale goes through all the letters of the alphabet and ends in 3 figures. In the base 5 task, the scale goes from A to E, but ends in 5 figures. Here is an example task. The index VBF had to be placed on a scale. There were 9 bins, from which each participant got a random sample of indices. The bins were equally spaced, except for the oversampling of the beginning of the scale, because we expected there to be the most volatility in estimates. If you want, you can make a guess on where the index would lie. If I go after my first thoughts, when I was not too familiar with the task, I would estimate the position to be around here, close to the end of the scale. However, the correct position is around here. This is because the 3-figure segment of the scale actually spans almost all of the scale. The 1 and 2-figure segments together only make up a bit more than 1/27th of the scale. We conducted the experiment as a between subjects design, with one condition for each scale to avoid training or carryover effects. To guarantee data quality, we employed 1 attention check and 4 instruction checks, which were designed to check if participants understood the instructions and the scale. We recruited participants from Prolific, and the final sample included 188 participants. The study was pre-registered on the Open Science Framework. We used the following models to analyze the data. I tried to keep this simple, so there are only the base models here. First, we set up a power model in which we fitted the exponent b. If there was compression, we expected the exponent to be smaller than 1. The linear model is the standard linear regression model, in which the scaling factor a is fitted. For the logarithmic model, fitting the base or the scaling factor is very similar. Fitting the scaling factor is easier to implement, so that is what we did. All of these models were fitted to the data in R using BRMS, using a fixed intercept at 0 to avoid predictions falling off the left end of the scale, and with participant random slopes, allowing for participants to have different levels of compression and accounting for repeated measures. Finally, the simple model is sequential linear and does not have any free parameters. This means it does not have to be fitted. I will shortly explain on the next slide. Most importantly, use the cross-validation approach to compare the prediction quality of the models. For this, we split the data in 5 parts and fitted the models to the training dataset, which was 4/5, and then predicted the remaining dataset. Repeating this for all 5 combinations and then for all 100 repetitions, we averaged the root mean square error for the individual participants. This lets us compare which participants are predicted best by which model. Before getting to the results, I'll walk you through an example of the simple model. This is an example for the base 26 scale with 3 figures going from A to ZZZ. First, we can easily calculate the actual position of the switch points on this scale. With switch points, I mean the start of a new scale segment after an element has been added. In the decimal system, that is 0, 10, 100, and so on. In the alphabet system that we used in our task and in which we did not include a 0 element, that is A, AA, and AAA. Then we are interested in how the position of the switch points is estimated by the participants, the estimated switch points. These are the ones I already talked about before. To get them, the endpoint of the scale is divided by the number of figures, allocating equal space to each segment of the scale. If we are interested in the actual function specifying y, we can simply divide the height difference between these 2 estimated switch points by the length difference of the actual switch points to get the slope. This is nothing else than y equals delta y divided by delta x times x. Now this thing here is the intercept, and in the brackets by the x, we are simply guaranteeing that x starts again at 0, so that the slope does not need to be adjusted. On the left, the function for the very first segment is a special case, since it does not need an intercept, and it does not need any correction of x as it starts at 0. I'm sure there is a more elegant way to do this, but this is what worked for us. So that is the simple model. Time to see the results on which model does best in predicting the participants' estimates. The gray lines indicate the individual participants' estimates. Each line is a participant. The different line types indicate each model as fitted to the whole dataset. So the left part does not yet show the results of the cross-validation. This is what the plots on the right side do. Each point indicates one participant's individual root mean square error as per the cross-validation. On top of the columns, you can see the percentage of participants best fit by each model. Based on the left plots, it is already visible that there do not seem to be any linear or power function shaped estimates. In fact, the power function was fitted with a best fitting exponent larger than 1, indicating that the model could not predict the estimates observed while assuming compression. A sign test confirmed that the simple model and the logarithmic model are the clear winners. They do not differ in performance, but both of them predicted more participants better than the other 2 models. So, what does this mean for our hypotheses? We found that subjecting adults to an unfamiliar place value system leads to estimates looking like the estimates that we have seen in children. And we found that a simple model, which assumes insufficient understanding of exponential growth, can predict the estimates on differing tasks remarkably well without needing any free parameters. Based on our results, we derived the following implications. First, we think that compression and symbolic number perception looks different from compression and non-symbolic number perception because symbolic numbers are denoted in the decimal system, and the place value of the decimal system is often not easy to understand. Second, we think that the compression which leads to the different patterns in both domains probably does not happen on the same level. Finally, we think that adults do not have a linear perception of symbolic magnitude independent of the underlying place value system. If they had, they would have been able to place the indices on the ruler in a more linear fashion. Why does this matter to you? Because if participants in your studies have to deal with numbers, it is important to know how they perceive them. With this, I would like to conclude. Thank you very much for your interest. A special thank you to my supervisor Benjamin Scheibehenne and my collaborator Markus Lenskau. And that's it.